Hi, good morning. My name is Oliver, and today we are going to conduct an experiment to determine the fairness of this rolling die, meaning each face of this die has an equal probability of facing up, basically. So we are going to go right ahead and start up with our experiment. So to begin with, I have a paper here which has the number of the die of each face from 1 to 6 and the frequency. So what we'll be doing is we'll basically roll this die 100 times, and we will, for each row, we will actually record the frequency of the appearance for each face. And I'm also gonna use a test statistic, basically called a chi-squared statistic, that will help us determine or compare the observed frequency of each appearance of this die with the expected outcome if the die was fair, basically. So I'm gonna go straight ahead and start. There we are done. So I just finished getting the 100 counts. So what I will do is I will go ahead and count the frequency of appearance for each face. Okay, so we are done recording our observed frequency, which you can see here. It goes from 14, 10, 18, 19, 22, and 17, which gives a total of 100. So the next step is we are going to conduct an experiment using a 5% significance level. So we'll have our alpha equals to 0.05. This significance level basically means that we are allowing 5% chance of rejecting the null hypothesis if this one is true. So given we have a 5% significance level, we'll go straight ahead and calculate test statistic. So the formula for a test statistic is x squared equals to summation I to n of the observed minus the expected over the expected all squared. So, but let's recall that we are dealing with each phase of the rolling die having an equal probability of showing up. So uh, I expected for each of them will be normally it's 1/6, but since we are rolling 100 times, it's gonna be 100/6. So doing 100 divided by 6, we get 16.67. I'll do 16.67 for our expected. So each of them have an expected chance of 16.67. So we will calculate the expected for each of them. It's gonna be I of 1. It's gonna be the observed. So actually, a test statistic will be x squared equals to the observed of each, which is, let's say for number 1 we have 14 minus 16.67 all over 16.67, and having our numerator squared, plus for phase 2 is going to be 10 minus 16.67 squared all over 16.67, plus 18 minus 16.67 squared all over 16.67, plus 19 minus 16.67 squared over 16.67, plus 22 minus 16.67 squared over 16.67, plus 17 minus 16.67 squared over 16.67. Now let's get a test statistic, the result of the summation. So now I've gotten my after computation, I've gotten my test statistics of a test statistic of 5.246 right here. So the next step basically will just be getting a critical value and being able to make a decision rule. So let's go ahead and get a critical value. So a critical value will be obtained from looking at the chi-square table for looking at the corresponding degree of freedom with the corresponding significance level. So the degree of freedom here will be degree of freedom is going to be 6 minus 1, which is equals to 5. So we have a degree of freedom of 5, and 6 is because we have 6 observed, or we have 6 categories, I would say. And then basically the formula for degree of freedom is k minus 1. That's k category minus 1, which gives you 5. So since we have 5, and then we have our alpha, which is equal to 0.05, now we need to look at the chi-square table and get a critical value with degree of freedom 5 at 0.05 significance level. So looking that up here, let me bring it. So looking that up here, we are trying to get, here's a degree of freedom, we have a degree of freedom of 5. Now right here we can get a significance level. We are looking for 0.05, which is right here. So degree of 5 at 0.05 significance level will be 11.071. So we technically have a critical value which is equal to 11.071. So now to make a decision rule is basically simple. We are going to compare a critical value with a test statistic. So if the critical value here is I'll say if the test statistic right here is greater than the critical value, then we will go ahead and reject the null hypothesis. Whereas if the test statistic here is smaller compared to the critical value, we'll fail to reject the null hypothesis, because prior to that we first had a hypothesis. The null hypothesis was, just to recall, it was the die is fair, and the alternative hypothesis was the die is not fair, basically. So we have it right here, and doing the comparison, we can observe that a test statistic is actually smaller. So after comparison, we see that a test statistic is actually smaller. So 5, I'll say x squared equals to 5.2465 is less than the critical value, which is 11.071. Considering this, then we will fail to reject the null hypothesis. Therefore, we fail to reject the null hypothesis. Since we fail to reject the null hypothesis, what does that mean? Because the alternative hypothesis was that the die is not fair, right? So meaning that there's at least one phase which doesn't have a 1/6 probability chance of appearing. So since we fail to reject the null hypothesis, this basically means that the die is fair, technically. So this means we do not have enough evidence to prove that the die is not fair, and therefore the die is fair. So each phase of the die has an equal probability of a snap. There we go. So we are done with our experiments. Thanks.